All right, lesson number 22. This is posted May 27th. If you are watching it that week, we have quiz number 3 on Wednesday, May 27th. Friday, May 29th, we have a review because test number 3 is on June 1st. That's Monday. It'll cover lessons 13 through 21. If you have questions, go to that review. I have a video posted that has information on all these things. A reminder that homework 19/20 is due on Wednesday, 21 on Friday. The homework for this one is actually going to be combined with lesson number 23, and that'll be due June 3rd. All right, looking a little bit ahead, June 10th, that's our final. The final will be on everything, okay? So we're on lesson 22. We have 5 more lessons, so we have 22 through 26. Those will be on the final along with everything we've done before this. Okay, so last section we were talking about acids and bases a lot. Remember, acids donate H+, bases accept H+. And then we talked about strong, which fully dissociate, versus weak, which are partial. Okay. Now we're going to talk about what happens when they come together. And this is called neutralization. Neutralization is when an acid and base react to give water and a salt. For instance, if I have HCl, that's an acid. NaOH, that's a base. These are both strong. So what they're going to form is they're going to form NaCl, which is aqueous, and water. This NaCl is called a salt, right? A salt is an ionic compound formed from the reaction between an acid and base, right? Okay, so for instance, here's my HCl. It fully dissociates. Here's my NaOH. It fully dissociates. When they come together, I get my H plus OH minus. And what's going to happen? These are going to form H2O. All right. So we call something neutral if we have equal amounts of H plus and OH minus. Okay. We're going to talk about 2 different types of things involving neutralization. The first is something called a buffer. And then later we're going to talk about titration. Okay. Titration is something you did in 215 lab. We've talked about in 216 lab. We're going to go through it now. Okay. In a next lesson, actually. Right now, we're going to talk about buffers. A buffer is a solution that contains a weak acid and its conjugate base. For instance, HF, a weak acid, and F minus, which is its conjugate base. Or a weak base and its conjugate acid. Okay? For instance, NH3 and NH4 plus. Okay? Now, a lot of times, I should notice that when we produce these buffers, we actually put the ions, those conjugates in there, as an actual salt, right? So if I put NaF into water, anything with sodium is soluble, so I'm going to get F minus out of it. And if I put NH4Cl, ammonium chloride, in water, I'm going to get ammonium ion out of it. Okay. The reason for this is it's impossible to have NH4 plus by itself. It's just not possible. I have to have something that is negative, such as ammonium chloride. Okay, so that's what a buffer is, but why do we care? We care about buffers because they resist a change in pH when an acid or base is added. Okay, let's explain this. Here's my buffer solution, and all of a sudden I'm going to add some acid or base. Adding in acid or base usually will change the pH a lot, but what happens is it ends up changing very little. For instance, let's show something that's not a buffer, right? Pure water. If I have 1 liter of water, pure, it's going to have a pH of 7. And all of a sudden, I'm going to go ahead and I'm going to add in 0.01 mole of HCl. That 0.01 mole of HCl is going to give me 0.01 molar H+, right? Because HCl is pure. I have 0.01 mole in 1 liter. All right, if I figure out the pH, this is getting pH 2. Okay. Notice, this is not a buffer. I added an acid and my pH changed by a lot. Okay. Let's say instead of pure water, this was blood, right? If I had 1 liter of blood, that's around pH 7.4, and all of a sudden I added in some HCl, I would get a very small pH change. It would still change, it'd become a little more acidic, but it's only going to go down by 7.3. Okay. If instead I added in a base like NaOH, my pH would go up, but it's going to go up very small amount. Okay. Blood is a buffer. And that's actually a good thing because, my blood, what's the job of blood? It's supposed to take oxygen and other nutrients to the cells, right? But if my pH in my blood was really high or really low, it would cause damage. In fact, a pH change of more than 0.04 in our blood can be fatal to our cells, okay, and then fatal to meat. So blood is a buffer. It's a good thing. How is it a buffer? It's a buffer because it has 2 compounds in it. It has H2CO3, right, known as carbonic acid, and HCO3 minus, okay? And this is an acid and its base. And these are a weak acid and a weak base, so they form a buffer, okay? And this is key to it, right? The Ka for CH3CO2, and that's just an example of a buffer, okay? So now let's go ahead and look at a different buffer. Let's say we have a buffer with 0.1 molar acetic acid, that's CH3CO2H, and 0.1 molar sodium acetate, right? Sodium acetate is this compound. When it goes into solution, it forms sodium ion and then CH3CO2 minus. Okay. This acid has a Ka of 1.8 times 10 to the minus 5. It's weak, okay? Let's say we go ahead and we add in some acid. What's going to happen? Well, if I add acid, that means I'm adding in H+. Notice I'm adding in a product. So what's going to happen? That H+ I just added is going to react with the base, okay, in order to form the acid, right? And none of the added H+ will be present, right? So basically, the buffer, the base in this case, acts as a way to remove that acid. Let's say instead I added in a base. Well, that base is going to react with the acid, CH3CO2H, and it's going to actually steal away a hydrogen to form H2O, and I'm going to be left with that acid, or that conjugate base, okay? And none of the added OH minus will be present, right? So acids and bases basically act to remove, or buffers act to remove any extra acids and bases, okay? All right, let's look at this one other way. Let's say we add this. Here's my acid, here's my base, okay? And let's say I start off with equal concentrations, right? So equal amounts. All of a sudden, if I add in H+, that H+, which is an acid, reacts with my base, and it's going to form an acid, okay? And so what happens is this CH3CO2 minus decreases, whereas the acetic acid increases. Okay? Instead, if I add in OH minus, that OH minus, which is a base, reacts with acid, okay? So the CH3CO2H decreases, whereas the acetate, the CH3CO2 minus, increases, right? So they basically do a teeter-totter, right? One increases, one decreases to remove whatever I add. Okay? All right, so let's just make sure we understand buffers by doing video problem 22a. 22a asks, which of the following are a buffer solution? Right? So remember, for a buffer solution, I have to have a weak acid, weak base pair. Okay? I can't just have a weak acid and a weak base. They have to be related to each other. Okay? So go through these, see if they're related, and see if they actually form a buffer. Okay? I have one hint at the bottom. Often it says we add conjugates as soluble salts, right? And this actually becomes important in this one right here, right? This NaHS, it's going to go ahead and it's going to form Na plus and another compound. And see if that compound helps you out. Okay, so now that we've talked about what buffers are, let's go ahead and let's do some problems, okay? All right, so we're going to generalize this a little bit, and we're just going to say HA, that's my acid, and A minus, that's my base, okay? So typically we have HA going to H plus plus A minus. And this is equilibrium, so we have it going both ways. And this is represented by AKA. Right? So if I add H plus, it reacts with that A minus to form HA. And if I add base, it reacts with the acid to form the base. Right? So we always get acid and base reacting. An acid won't react with another acid. A base won't react with another base. Okay, so we're going to go through some problems, both this lesson and next lesson. Or we're going to go through one problem, but in multiple steps, right? So let's say we have that buffer with 0.1 molar acetic acid and 0.1 molar sodium acetate. We're going to figure out what its pH, what happens if we add acid, what happens if we add base, and then finally we're going to say, can we add too much? All right, so let's figure out its acid. Okay, so before we do this, let's go ahead and let's think of this reaction. We have CH3CO2 CH3 CO2H. Okay? This is an acid. It's going to react to form H plus plus my base. Okay? This has a Ka. Well, if I want to figure out what's going to happen, I could use an ice table, right? I could say, okay, I start off with 0.1 molar of this, start off with 0.1 molar of this. Let's go ahead and do that entire ice table. But instead, we have a simpler way to do it. And this is something called the Henderson-Hasselbalch equation, okay? Or a lot of times I just write down HH equation. The Henderson-Hasselbalch equation figures out the pH of a buffer. All right, so in order to do this, let's just remember what Ka is. Ka is H plus times CH3CO2 minus over CH3CO2H. Okay? This is just the definition of what Ka is. Now, if I want to go ahead and rearrange this for H plus, okay? Oh, by the way, before I do this, let's go ahead and just generalize this to say Ka equals H plus times this. I'll just call this the base, and I'll call this the acid. Okay? And let's rearrange this for H plus. So H plus is going to be Ka times the concentration of HA over A minus. Okay, I just rearranged it. Now, what is pH? Because remember, our question's asking for pH. pH is the negative log of H plus. So that means pH is going to be the negative log of this. Okay? So negative log of Ka times Ha over A minus. Okay. All right, now it ends up that there's a rule for logs. And that is that if I have something log of something times something else, I can just add these up, right? So I could separate this into negative log of Ka minus the log of Ha over A minus. Okay. Well, negative log of Ka, we already know this as pKa. Right? And there's another rule for logs, which is if this is negative, I can flip these, and this will become positive. Okay. And so I have this equation here. Right? That the pH for a buffer, and this is for a buffer only, don't use this for just acids or bases, the pH for a buffer is equal to the pKa for the weak acid plus log of the concentration of my base over my acid. Okay? You don't need to know how to use this term, right? But you should know, you should get used to using it, okay? Or this equation. It's very useful when we do these calculations. All right, so a few things on the Henderson-Hasselbalch equation. It only works if x is small, right? It only works if you're not adding a whole lot of the acid or base. It only works if you have really high volume or concentrations of your acid and base, right? Such that they're so much bigger than your Ka. I'm going to tell you this, in this class, they're always going to be bigger. So it will take place if it's a buffer. The other thing we should notice is, notice this is moles per liter over moles per liter. Well, seeing that this is a solution, the liters of that solution is going to be the same. So I can just cancel that out, right? So I can say that pH equals pKa plus log of the concentration of base over acid, or log of the moles base over acid. Which one I use depends on what I want to do. Okay? All right, so let's do this. Let's use Henderson-Hasselbalch in order to find the pH of this buffer. All right, so we're told that, so we're going to do pH equals pKa plus log. What do we have there? We have molarities, so we'll just use that. So my pKa is negative log of Ka, which is 1.8 times 10 to the minus 5, plus log, okay, A minus is my base. So which one's my base? That's the acetate, okay, which is 0.1 molar, over my acid, which is also 0.1. So in this case, it doesn't matter. 0.1 over 0.1 is the same as 0.1 over 0.1. But make sure it's always base over acid, right? Base, acid. All right, so this will be the negative log of 1.8 times 10 to the minus 5 is going to be 4.74. This will be log of 1. The log of 1 is 0. Okay? You should know this or get used to this. We'll use this a couple times. Right? All right, so that means the pH for my buffer is 4.74. Okay, so I'm able to use the Henderson-Hasselbalch equation to figure out pH without using an ice table. Okay, anytime you can get away without using an ice table, you do it. Okay, now remember this is only for buffers, right? On test number 3, we're not going to use this because we're not talking about buffers, right? And buffers are only when we have weak acid, weak base pair. Okay, so that's my initial pH. Let's go ahead and figure out what happens once I add some acid. Okay, so if I add acid, so the acid I'm going to add is 1 ml of 0.1 molar HCl, and I'm going to add that to 100 mLs of buffer. Okay? Okay, so here's the key on buffers. I'm adding acid, so it's going to react with base. Okay? So which one of these compounds is it going to react with? It's going to react with my base, which is the CH3 CO2 minus. Okay? Remember when we're talking about equilibrium, and so as Q goes to K, if we have an acid, it's going to react with a base. Okay? And so once these two react, it's going to form CH3 CO2H. I promise it'll be on the next page. All right? All right. Here it is. Oops, let me erase some stuff. Right. So my acid that I just added, the H+, reacts with the base I have in my buffer, and that goes ahead and forms the weak acid. Okay. All right, so in order to do this, we're going to do something similar to an ice table, but not quite. And we're going to do this because we're not actually going to go to equilibrium. And remember, equilibrium, that's an E in ice. And we're going to actually use moles instead of molarity. Okay? So the first thing we have to do is we need to figure out the moles of each compound. Okay? I'm going to do this on the board. Okay, so I have CH3, CO2H. Sorry. I have CH3, CO2 minus, plus H plus, going to CH3, CO2H. Okay, I'm not going to write this as an equilibrium because this reaction actually is going to go all the way to this. Okay, so when I add in that acid, it's going to go all that way, and then it's actually going to equilibrate a little bit. But I'm going to assume it goes all one way. All right, so I need to know the moles of each one of these. Okay, so let's start with the CH3 CO2 minus. How much of that do we have initially? Well, we're told we have 100 mLs of buffer, and that buffer contains 0.1 molar sodium acetate. So I need to make sure to make this in liters times 0.1 molar. That's going to give me 0.01 moles. Okay? So that's how much of my acetate I have. The calculation is actually the same for my CH3 CO2H. And how much of my HCl do I have? Well, I've told you that I'm going to add 1 ml of 0.1 molar HCl. Okay. So that's going to be 0.001 liters times 0.1 molar. That's going to get me 0.0001 moles. Okay. All right. So now we're going to go ahead and we're going to look at this some more. All right, here they are on the screen. You can see that we basically have to figure out all 3 moles of each component we have in that reaction. And now what we're going to do is we're going to make an ice chart, okay? But it's not quite ice. So we're going to have our initial, we're going to figure out our change, and then we're going to have our final. We're actually not going to do what we usually do, which is a Q, right? Here we're just going to say that what do buffers do? Buffers remove all the H+. So this is going to go down by 0.0001, right? It all gets removed. And so if this gets removed by that much, this will also get removed by that. And then this will increase by that same amount, okay? Why does this have to increase if these decrease? Because of the law of conservation of mass, okay? All right, so once that happens, we get 0.0101. We get 0 for this, and then we get 0, oh, sorry. I added here instead of subtracting, and this becomes 0.0101, right? So basically adding in that H+, switched it so I have a little more of my acid here, okay? Now what do? Now I can just use Henderson-Hasselbalch equation to figure out my pH, right? So my pH is going to be equal to my pKa plus the log of my base over my acid. Notice these are in moles, and if I look at the top, I can use either molarity or moles. Here I'm going to use moles, right? All right, we have our Ka that was given to us earlier. Let's go back. It's 1.8 times 10 to the minus 5. By the way, we already did this, but I'm just keeping it. So that's plus log of 0.9802. This is going to get me 4.74. Whenever I have log of 1 equals 0, log of anything below 1 is going to give me a negative value. Right? So if I take the log of this, I get negative 0.0087. Okay. So what's going to happen? My pH is going to end up as 4.73. Okay. Does this make sense? Yes. Because I start off with a pH of 4.74. I added in acid. So what's going to happen to my pH? It's going to be lowered. In this case, it gets lowered a very small amount. Okay. All right. Here is an example of that chart. We have moles of each compound. We put it in there. And remember that in buffers, all the H plus or all the OH minus gets moved away, right? So I end up with these two values. I then can put those into Henderson-Hasselbalch equation, and I get my new pH, okay? So I went from 4.74 to 4.73, right? The buffer didn't stop the pH change, but it made that pH change very small. Okay? All right, let's go on and let's think of instead of, so in part 2, we went ahead and we added an acid. Let's here say instead of adding an acid, what if we add a base? Okay, so I'm going to take my buffer. My buffer has an acid, HA, and it has a base, A minus. And now I'm going to add in some OH minus. Which one of these is the OH minus going to react with? Is it going to react with the HA, or is it going to react with the A minus? Well, it's a base, so it's going to react with the acid. Okay? And what happens is it goes ahead and it steals an H plus, so that gives me A minus, and I'm going to be left with H2O. Okay? This, a base and a base, that's not going to react. Okay? All right, so that's my reaction, right? My acid reacts with a base to form the CH3CO2 minus. Okay? All right, so let's now use that equation in order to figure out the pH after we do this. All right, so we have CH3CO2H plus OH minus goes to form CH3CO2 minus. What do I have initially? Well, I have 100 mLs of buffer. We already did this calculation, so I have 0.01 moles of each of my buffer components. Okay? And now I'm going to go ahead and I'm going to add in some NaOH. Okay? I add in 1 ml, or 0.001 liters, of the 0.1 molar solution. So that's going to get me 0.0001 mole of my OH minus. Okay? All right. So what's going to happen? Well, this is all going to go away. So this is also going to be reduced. Okay? And this is going to increase. So then at the end, not at equilibrium, but at the end of this reaction, I'm going to get 0.0099 moles of my CH3CO2H, my acetic acid. I'm going to get no OH minus, and I'm going to end up with, 0.0101 mole of this. All right, and now I'm going to go ahead and I'm going to use Henderson-Hasselbalch equation for this. So the Henderson-Hasselbalch equation says pH equals pKa plus log of my base over acid. Okay. We already found the pKa last time. That was 4.74 plus the log of my A minus over this. And that's going to be 4.74 plus, whenever I take the log of something greater than 1, it's going to give me a positive value. In this case, it will be 0.0087. So that's going to get me a pH of 4.75. Right? Does this make sense? I start off at 4.74. I ended at 4.75, and I did this by adding base. So it makes sense that when I add a base, my pH is going to increase. It becomes more basic. Okay. Here it is on the screen. I go ahead. I start off with my moles of each. I figure out how they change, and the key is that in buffers, when I add an acid or a base, it all goes away. Okay. And then I end up with my final concentrations of my acid and my base that are in the buffer, right? Remember, this isn't in the buffer. This is changing the buffer. These two right here, these are the components of my base. So these are the ones that go into my Henderson-Hasselbalch equation. Okay? All right, so I get 4.75, and that's when I add in some base. Okay? All right, so that's it for lesson number 22. We're about halfway through looking at buffers. Okay? So remember, a buffer is a solution of weak acid and its base. Okay? We talked about the Henderson-Hasselbalch equation. For this lesson, we'll do video problems 22b and c. Those will be dealing with it. And then we started talking about what happens with acid when we add in some acid and base. We're going to deal more with this next lesson, and we'll do some problems with that. Okay? But for now, I'd like you to do video problem 22b. This is using the Henderson-Hasselbalch equation to find the pH of a solution containing HF and F-. Notice, you need to know pKa. I didn't give you Ka. I gave you Kb. How do I go from Kb to Ka? We learned that when we're dealing with acids and bases. Okay? All right, and then 22c, I ask, you want to make a buffer with a pH of 4.15. You have these two components. You have HA, you have an acid, and you have a base. Okay? And we want to know what the mole-to-mole ratio of base to acid you need. Okay? This is a little bit different than 22b, right? Notice in this one, you're given pH. You can calculate pKa. And what's it asking for? It's asking for this ratio, this base to acid ratio. This is what you're trying to find, okay? So plug in your pH, plug in your pKa, and try to find this A- over HA, okay? You're going to have to remember what the opposite of log is, and that's 10 to the x, okay? It's on your calculator. All right, so that's it for lesson number 22. Remember the homework for this. This one doesn't have a homework itself, but this is incorporated into the homework number 23. That'll be on buffers. Okay, we're on the home stretch. We have this last week of May, the first week of June, and then we have final. Right, so make sure you're continuing on with the homework, doing the labs, getting all the points possible. And the final is Wednesday, June 10th. I'll tell you all about the details on that, but it's going to cover everything, not just new material, but everything going back all the way back to, oh my goodness, what did we start with? Started with talking about heat and thermal chemistry. So all that's going to be on there. All right, but before then, June 1st, test number 3. All right, with that, I'll talk to you later. Bye-bye.